Subject Advanced Structural Mechanics, and the topic is Engineer Beam Theory. The assumptions are the plane section of the beam remain plane. The material in the beam is homogeneous and obeys Hooke's law. The modulus of elasticity for the tension and compression are equal. The beam is initially straight and of constant cross-section. The plane of loading must contain a principal axis of the beam cross-section, and load must be perpendicular to the homogeneous axis of the beam. These are the assumptions for engineer beam theory, and engineer beam theory is good for ordinary beams which have got cross sections very small as compared to the length if we have deep beams. So in that case the engineer beams theory may fail. Our engineer beam theory gives us wrong answers. So for those structure we will develop the theory of elasticity. Okay, so from that point you guys have to understand that engineer beam theory is just for uh, normal beams, ordinary beams, so which have got cross sections very small as compared to the length. Okay, the second assumption, which is material is homogeneous and obeys Hooke's law. uh, it means that the material uh, the homogeneity of a material means that the material is continuous and cohesive. In last video we talk about that concepts. The molecular arrangement of uh, of of the material should be in that uh, in a way that it it shows the properties like it is cohesive and continuous. Okay, we discussed that the stress equation is derived from a body which is homogeneous, and homogeneous means that the body is continuous and cohesive. Yeah, here it is also explained to you. Continuity of a body means that there are no cracks and gaps in the body. The body is continuous, okay, and the body has got a uniform surface. Cohesiveness means that the molecules making up the whole body are uniformly distributed around the body. Okay, note that these are the assumptions. These assumptions uh, should uh, these assumptions are important to be noted. Okay, while you are working on engineers beam theory, so these assumptions are important. The molecular structure has no gaps or no voids. The whole structure is a solid mass. Okay, here we have assumed uh, a beam. Okay, so how can we derive Flexure formula using engineer's beam theory? So let's assume that the beam is now loaded. This is before deformation and this is after deformation when load is applied. So when load is applied, the beam bends like that. Okay, these 2 points A and C close together. Here I can show that this point and this point C, these 2 points close together. Okay, the above portion is compressed. In other words, you can say that the above surface is compressed, and these 2 points B and D moves apart. Okay, B and D moves apart, so this below portion is in tension. There is difference between centroidal axis and neutral axis. Yeah, definitely. Here you can see that there will be a line. Okay, we call it a neutral line or a neutral axis. So at that line you can see that it is written neutral axis is a line about which total force is considered zero in any body. Okay, here we can see that there is the total force on this line is 0. Okay, and the centroidal axis is a line which is passing through a point about which the whole weight is considered to be concentrated. Okay, centroidal line. uh, it may be possible that centroidal axis and neutral axis are same, but in some cases it may not. Okay, let's move. Let's consider we are interested in finding out the extension of a fiber which is located at region x2 from neutral axis. Okay, we have considered a fiber, this fiber G and K. You guys can see that we are interested in this fiber extension. Before loading, this fiber is just straight, and after loading, this fiber extended. As we know that this portion is in tension and this is extended. So G and K, this fiber, we are interested in this fiber. So strain, we know that strain is change in length divided by original length. So change in length from this figure, you can say that what is change in length? First, the fiber was this was the original length. You can see that this was the original length, BD. Okay, so as we know that the line neutral line stays the same. It's neither extend neither compressed. So if we draw a line, okay, that is like in this way, so this line will cut from neutral axis. We'll draw a line. It will cut d dash. So this is the original length. Okay, this is the original length from from this point. Let me show from this point to this point. This is the original length. Okay, and while this green is the change in length. Okay, so for the fiber, this original length will be this, and the change in length will be this. Okay, so we know that the strand is change in length divided by original length. So first, how we say a change in length is equal to x2 into d theta. So here is we are using a formula which is s is equal to r theta. We are using the formula. So uh, this 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 will be equal to del theta into x2 divided by original length. This is the change in length. Okay, this is the change in length, and gh is the original length. Yeah, definitely gh, this is the this is h, gh is the original length. So original length, this is the curve. Okay, so this is this we can gh is equal to ef. So these are same, gh and ef. I can show to you in a green that this and this and this is same. So we can say that this is d theta, okay, d theta into y will give you this ef, and this ef is gh. So gh is the original length, so it is equal to d theta into y. So y d theta, there it is. So we can cancel this theta by theta, and we got x2 divided by y. So the strain 3, or we can say strain 3 on a phase 3 and in the direction uh, 3. Okay, strength 3 means on strength 3 in the direction of 3, x2 divided by y. So this is strain. So stress is equal to E times strain, is modulus of elasticity. So here we got stress. Okay, we got stress. In this discussion, we will considering only those bodies which are at rest, and we are not considering any dynamic effects on the bodies. So we assume that the current body is also at rest. Yeah, definitely. We are considering only the uh, static conditions. Under these considerations, we have to say that there are six equilibrium equations which must be satisfied, and those six equations are summation of forces in all the direction and summation of moments in all the direction must sum up to 0. So we have this beam. Okay, we take a portion of a beam, we take an element of that beam. Okay, that it is, and it is shown in 3D. Okay, we have got loading plane, longitudinal plane of loading. We have got neutral axis. Okay, we have three directions: x2, x3, and x1. Imagine we taking small portion of a beam, and that small portion in the form of element cube. Please note we have got neutral axis uh, which is in x2 and x3 plane. Yeah, definitely. And we have got loading plane which is in the longitudinal plane in x2 and x3 direction.